Yeah, there we go. All right, so welcome everyone. Shure's lemma is among the first lemmas propositions we learn as we serious after we start learning math seriously, right? But obviously it's not the end of story. And today we have Tamar to tell us more about that. So there you go, Tamar. You have it.
All right, thanks. Yeah. Yeah. Okay. So yeah, I called this Shure's lemma and beyond because it's I do want to go through sort of like the classic Shure's lemma, especially in case anyone hasn't seen it. But even if you have, I think it's nice to review. But then I think sometime last year kind of found out more about Shure's lemma and how deep it runs, and it's really like a very I don't know, I think it's really pretty cool. So yeah. Okay, so well, I guess I'll tell you how I started like finding out more stuff about Shure's lemma. I mean, you learn it in like a representation theory course, or like, when you're reading some book, like kind of just comes up a lot. But I was reading a paper where there was this statement using Shure's lemma that was proving something about a quadratic form. So as I'll say in a minute, I mean, Shure's lemma is like a fact about, or we think of it as a fact about representations. So like how could you use Shure's lemma to prove something about a quadratic form? And I'll get back to this statement in shortly to like unpack it. But first I want to talk about Shure's lemma itself. Like this. Yeah. Okay, so this is Shure's lemma for group representations. I think a lot of people here have like read some of Humphrey's book on Lie algebras, and there's sort of the same Shure's lemma exists for a very similar looking thing exists for representations of Lie algebras. But I just decided to do the group version. I think it's maybe a drop simpler, and it happens to be what applies to this paper as well. So here's Shure's lemma. So first you start with a group and you take two different representations of the group. And these representations should be irreducible representations. So they don't have any non-trivial sub-representations. And suppose that I have a map of G representations. So that means, right, so phi from V to V prime is linear. But also, I guess I used the like row notation, but you could also say in terms of like the group action notation, G dot phi of V is equal to phi of G dot V, for any G in the group and any vector. So, okay, so that's the setup. Then we have that either phi is the zero map or phi is an isomorphism of representations. So I think it's possible that everyone here has like seen this already. And so you're like, okay, yeah, right, it's either zero or an isomorphism. But I think when you first see this, I think when I first heard of this, I don't know, it seems pretty surprising, right? Like these are they're irreducible representations, like, okay, but when you try to take the maps between them, they sort of all are this very plain thing. There's just isomorphisms. So that's like part A, and that is actually what I'm going to be emphasizing like later in the talk. But there is also a common part B, which is that if you take your field to be something algebraically closed, and now you have phi mapping just from the same representation back to itself, then phi is actually a scalar multiple of the identity. So like there's phi is equal to like lambda times identity, which like as a matrix would be, a diagonal matrix of lambdas for some lambda in the field. Okay, so that's the second fact. Before I guess I go on, I didn't particularly stop for questions. So first, does anyone have any questions? All right. Okay. If you have any questions and I don't stop for questions, feel free to interrupt because I'm always very happy to stop and discuss things. All right, so this is the statement of Shure's lemma, and now for the proof. Oh, there we do. Yeah. So the proof of part A, I decided, by the way, I'm going to do most of this is slides, which I'm just kind of going to be writing on. But I thought this proof I would do by hand because it's nice and it's short. So yeah. So first of all, okay, so what does it mean for a representation to be irreducible, right? So V and V prime are irreducible. That means, so V irreducible means that every subrepresentation of V, the only subrepresentations of V, I should have said only subrepresentations of V are 0 and V. So, and the same thing for V prime. So the trick with the proof of Schur's lemma is you notice that the kernel of phi, right? Because this is just it's a linear map. You can think about the kernel. It's a subspace, certainly of V, but it's actually a subrepresentation. And to prove that, I mean, you can think about, well, if V is some element of the, oh, right, and because a subrepresentation, right? If you haven't been thinking about representation theory lately, you might, like a reminder. So a subrepresentation is just a subspace that's closed under the action of every G in the group. So if V is in the kernel, right? V is some element of the kernel, phi of V equals 0. I need to show that phi G dot V is also equal to 0. And G dot V is also in the kernel. But because phi is a homomorphism of G representations, this is the same as G dot phi of V, which is G dot 0, which is equal to 0. And similarly, you can show that the image of phi is not exactly the same argument, but it's similar. Something like this you do is also, it's a subrepresentation of V prime. Okay, so that's our start. And now to prove this, I mean, I guess what I want to do is I'm going to go on to the next page so I don't squish this. I have kernel of phi is a subrepresentation of V. So kernel of phi is 0 or V, and the image of phi is a subrepresentation of V prime. So the image of phi is 0 or V prime. What are we actually trying to show, right? We're trying to show that phi is either 0 or an isomorphism. So if phi is 0, then we're done. And so I guess we can just assume phi is not equal to 0. Right? Are people okay with that? So if phi is not equal to 0, then what can the kernel be? Well, if the kernel of phi is all of V, then phi maps everything to 0, and then phi is a 0 map. So that would be a contradiction. And if the image of phi is 0, then again, phi maps everything to 0. It's the 0 map, so that can't be either. So now what this tells us is that, is that phi has kernel 0, which means it's injective. And the image of phi is all of V prime, which means that phi is an isomorphism. And yeah, so that's the proof of part A. Any questions on this? I'm actually going to hop back to the slide a little later because I want to point something out about the proof, but I don't think we're exactly ready for that yet. Okay. All right, so on to part B, and now we're actually going to use some linear algebra. So here we're taking an algebraically closed field, and phi is mapping V back to itself, the same representation. So here's the trick. If we have a vector space over an algebraically closed field, and we take a linear map from V to itself, then we always have an eigenvalue. So we let lambda be an eigenvalue for phi. This is because k is equal to k bar. It's algebraically closed. We can do this. So then I claim that phi minus lambda times the identity. So this is like the diagonal thing that we're trying to show these two maps are equal. And I'm claiming this is a homomorphism of G representations. So the way that you can see this is you can apply this to, so phi times lambda I. If you apply it to G dots acting on some element, well, this is phi of G dot V minus G of lambda times V. And this is, the G moves past the phi. I should put that on the next line probably, right? G dot phi of V minus, and lambda is just a scalar, so it comes out G dot V because G is acting by some linear map. And this is, wait, I have the have this backwards, don't I? Right, this should be lambda g over here and g lambda over here. So while I'm writing this, you can probably see where this is going, but lambda g dot v. And so right lambda moves past the g dot lambda v. I can't get this right. G dot lambda times v, parentheses. This is scalar multiplication. And this is just g dot phi, g applied to this vector, which is phi minus lambda I of v. So the whole point of this was just to show this is a homomorphism of G representations, and that's good because now we can say by Schur's lemma, part A, which I would argue is the main part of Schur's lemma, we get that phi minus lambda I is an isomorphism or 0. But because we picked lambda to be an eigenvalue, there's some non-zero vector v in the vector space such that phi of v is equal to lambda v, which means that phi minus lambda I maps some non-zero vector to 0. So it can't be an isomorphism. And since it's not an isomorphism, it must be 0. And so phi is equal to lambda I. So that's that. That's the proof of the second part of Schur's lemma. Yeah, okay, questions about this? The next thing we're going to do is like apply this to the quadratic forms statement, I guess. I wouldn't even say proposition, it was just kind of like casually thrown out there, as happens in papers. So, okay, so I just actually screenshotted this. This is from a paper by Skip Garibaldi. I was reading it. This is from the archive, whatever. If you want to see it, I put in my references if you want to look at the paper, but I thought I should like unpack some of the terminology here. So first of all, what does it mean for a representation to be absolutely irreducible? So the idea is that, so if you take, so K bar, the algebraic closure of K, is a field extension of K. So depending on what kinds of things you work with, you may or may not be familiar with like extension of scalars of algebraic objects as like a thing that people like to do. But the idea is that this is a vector space over K bar. And so you can act on it by G in the following way. So G can act on, if you take a simple tensor V tensor alpha, where this is a vector in V and this is some element of the algebraically closed field, this just is G dot V tensor alpha. And so you get an action on the extended vector space. And so what that gives you is from the representation over K, you get a representation over K bar. And when you start with something irreducible over K, you don't always get something irreducible over K bar. You can think of examples where things sort of break apart once you add more scalars. So absolutely irreducible means that doesn't happen though. When you extend scalars, you stay irreducible. The second thing that maybe not everyone has seen before is the idea of a quadratic form that's invariant under the action of a group, which means that if you take G and apply it to any vector, and then you take the quadratic form, you should get the same element of K as if you just did Q of V. It's actually, for a little while, I was trying to work with quadratic forms that are invariant under the action of a Lie algebra, and that's like much worse. It's like a much like weirder, more difficult thing to try and define, even though it does have a definition. Okay, so anyway, that's what that means. And what this is saying, this Q is uniquely determined up to multiplication by a scalar, is that if I take some other quadratic form that has this property of being invariant under the action G, that I should get that as functions to K, I should get that Q of V is equal to lambda times Q prime of V for some fixed lambda. And here I think it's assumed that these quadratic forms they're not 0, right? I guess I said that. So the lambda will be in K bar, K times the non-zero elements of K. All right, so this is the argument that I came up with. I haven't seen this somewhere, but this is what I think he meant by Schur's lemma, Q is uniquely determined up to a scalar. So this is the first thing, I guess. If you've ever looked at, I think it's chapter 3 of Fulton and Harris, there's this and it's in other books on representation theory as well. When you have a bilinear form that's compatible with the oh, I should say, actually, before I get ahead of myself, let me just say what I mean by v and v prime. So for any quadratic form over a field of characteristic not 2, which I guess I'm assuming here, there is so there's a bilinear form such that q of v equals b of v for all v in the vector space. And this is a symmetric bilinear form, so q prime of v. And there's like a correspondence here, v prime of v. And you can get from the bilinear form to the quadratic form as well. So what you can do is using a little bit of like funny business, just like interesting maps, where you can like go to the dual representation and come back. You can find a homomorphism of G representations, which is from V to itself, such that when the functions, take b v blank, so this sends w to the element of k b v w. Or I guess I don't want to say the functions, right? This means that like b v w equals b prime phi of v w for all v and b. Right? Does that make sense? So okay,
wait,
so yeah,
wait,
sure.
So for all
For all w and v, yeah.
Okay.
Yeah.
Thanks.
Sure. Yeah. So okay, fine. So from there, if you believe me, I mean, I'm happy to talk about this. I could talk about it at the end of the talk if you want. But it's a thing you can do. I can even tell you like where to find it in the book if you want. But okay, but the thing is that so V tensor K with K bar is, because our original representation was absolutely irreducible, this V K bar is an irreducible representation over an algebraically closed field. So we can map from V tensor K bar to itself. So this map that I called phi tensor ID is supposed to map for any, I guess, simple tensor, or you could extend it. It should map to phi of V tensor alpha. And this is a homomorphism of G representations because phi is. So what we get from the second part of Schur's lemma is that this is actually of the form lambda times I for some lambda in K bar. But if you think about the way this map is defined, if this is equal to multiplying by lambda, then this actually is going to have to happen in like the first piece. You get that lambda is actually an element of the original field, an element of K. And so what you get is phi is equal to lambda I. And then what you can say is that Q is equal to lambda Q prime, right? Just to write this out in terms of the bilinear forms, that Q of V is B of VV, which we, by the definition of phi, is B of phi of V, comma V. And from Schur's lemma, we get that this is lambda V, V, and then by bilinearity, this is lambda V prime V, V, which is lambda Q of V. That's the idea. So, okay. So this was kind of like part one of my talk for the following reason. This is something cool you can do with Schur's lemma, but it's also with like regular Schur's lemma. And before I figured this out, I was kind of just trying to figure out like, okay, they're using Schur's lemma for quadratic forms. Like, is there a more general Schur's lemma? And I guess maybe by coincidence, the answer is like very much yes. So what I want to talk to you about now is sort of the more general Schur's lemma, and something that might hint at there being a more general version of Schur's lemma, if I can find the slide. Yeah. So if you think about the proof of part A of Schur's lemma, which is now what I'm going to call Schur's lemma, probably for the rest of the talk, then what are we actually like using here, right? Like we're proving a statement about representations, which are like vector spaces that have an action of a group. There's these invertible linear transformations. But like we kind of just used like irreducibility and like kernels and images and zero. So what I'm arguing that you might think from looking at this proof is that like maybe if we can get other things that have kernels and images and irreducibility and zero that aren't representations, but just kind of have those concepts, we might be able to have a corresponding Schur's lemma. So let me go back. Okay, yes, a broader perspective. So if we can get these things, kernels, images, zero, irreducible, this isn't like an exhaustive list, but just sort of the kinds of things that you might think of, then maybe we can get another Schur's lemma that's sort of broader. And surprise, when you want to do things in general, you might want to use category theory. And in particular, the specific sort of category-ish structure that we're going to want to use is something called abelian categories. Okay, so when I was writing this talk, I wrote a slide that had the definition of an abelian category on it, and I decided not to use it. I mean, you can see it later if you want, but the problem with the definition of abelian categories is that it's really long, and then when you look at it, it's like not super enlightening, and it's also not super obvious how or if all this actually will play into our Schur's lemma stuff. So what I decided to do is give you some examples of abelian categories. If you have learned what an abelian category is, then great, you'll know. And if you don't, I'll also tell you like some properties, like some things about abelian categories that will be useful to know, I guess, and relate to the Schur's lemma stuff. Part of why I like this, by the way, also is besides for it being like, oh, there's something you think is Schur's lemma, but it's actually big, really lots of math. It connects to lots of different areas of math, but also because this is like, you're using category theory and you get something that's not category theory, which is like, it's always fun when that happens, Okay, yeah, so here you go. So these are some abelian categories, just like some examples, right? I didn't tell you what an abelian category is, but here are some categories that are abelian categories. And the first example is the category of abelian groups. And when I say, category of abelian groups, I mean like, I just told you the objects and not the morphisms, but I mean, you might expect this is with group homomorphisms as the morphisms in the category. You can think about if you have a ring, it doesn't even have to be a commutative ring, but you can think about all the modules, the left module R modules, and the R module homomorphisms between them. And that gives you a category, which also turns out to be this thing we call an abelian category. And if you take, in particular, if you take that ring to be a field, you get the vector spaces. Just another example. Vector spaces and with linear maps, those are the morphisms. This is a more complicated example, but I wanted to include it because I think it's good to see things that are a little bit different. So I don't know if everyone here has like seen the definition of a sheaf or not, but a sheaf is a way of, so in this case, a sheaf of abelian groups. So here, if you take a topological space X and you think about all of its open subsets, then a sheaf is some way of assigning an abelian group to each open subset in some sort of like nice, structured, compatible way, which I will not give you all the details of right now. And I think in some way it's supposed to generalize like the idea of functions on a space. Like people give the example that like you have a sheaf of like smooth functions on a manifold or something like that, but that might not be exactly right, I'm not sure. But one of the reasons that I think this is a good example is because it's not, a sheaf is not just like a set with structure the way that like a group is. Like a group is like a set, but you can like multiply things, and a sheaf is a little bit more complicated, but it still happens to be one of these abelian categories. And one last example, last but not least, that I'll put on this slide is the category of representations of a group over a field. I guess I put the complex representations here, but it could be any field that you choose. Ends up forming an abelian category, which shouldn't be a surprise because we're trying to take something from representations and generalize it to abelian categories. All right, so the other thing I wanted to tell you about abelian categories was just like some of the things about them, some of the properties, part of the definition, but not literally everything. So, okay, so the first and pretty important feature of abelian categories is that you get abelian groups when you look at the maps between any two objects. So there's some way of adding, sort of adding functions, adding morphisms between any pair of objects. And you also have this property that composition distributes over addition. So you can think of it as like the abelian group structure is sort of compatible, but in this particular way, where if you take like f plus f prime, so this is the addition in hom a comma b, and you compose with some g, where g is, I don't know, from z to a or whatever. This is f compose g plus f prime compose g. And similarly, h compose f plus f prime is h compose f plus h compose f prime. So this is sort of like a very logical abelian group structure. And if we just look back at our examples for a second, like when you have two group homomorphisms between abelian groups, you could sort of add them pointwise. If you have two linear maps, you can add them again like pointwise. There's like this notion of adding functions. Another thing about abelian categories is that every abelian category has what's called a zero object. So if you want like category language, that's it's an object that's initial and terminal. But if you don't want category language, then you can think of like the abelian group with one element that's like 0, or the 0 vector space, or something like that. But this is useful, right? Because we were talking about Schur's lemma, we have like 0. We want to make sure that 0 is the thing that sort of makes sense. I guess 0 maps are really the thing that we were talking about. So it's not exactly the same, but whatever. I guess 0 like sub-object. Yeah. Okay. Another thing that we're going to need though is we had these kernel and image situation. So because we're just working in this like arbitrary kind of, or like vague sort of category framework, kernel and co-kernel aren't necessarily going to mean like the exact familiar things that we think of, except if we are working in like the abelian category definition of kernel, if we bring it down to something like abelian groups, it will like work, but they're defined in sort of an interesting way. And like, for example, the image is not like a thing that's defined by itself, but it's defined as like the kernel of the co-kernel of phi, I think. It's like a little complicated. We're not going to go into the details of how these things are defined, but you have some sort of idea of a kernel and image, which is what's going to matter for us. And one more thing, which is that there's this notion of a monomorphism, which is like a stand-in for the notion of injective, right? Because the problem is that the things we're working with might not just be sets. They might like sets with structure. They might be a little more complicated. So we can't say injective, but we can say monomorphism, which is defined in like a not elements-y way. And from the notion of a monomorphism, we can get an idea of a sub-object, which brings us to what we want, which is simple or irreducible objects, right? Things that don't have any sub-objects besides themselves and 0. So, okay, that was like a little tour of like some of the things that come up in abelian categories. But the reason I even wanted to introduce this was to sort of do the general Schur's lemma. Oh, but before I do that, I wanted to tell you, actually, I wanted to just for like, I guess, the purpose of illustration, I thought maybe it would be good to do just the technical definition of one of these in case you haven't seen or studied abelian categories before and you kind of want to like get a taste of how these things are being defined, because I think it's a little weird until you get used to it. So if you have an abelian category A, and you have objects, A and B, and the morphism F from A to B. So again, this is like it's not like it takes elements in A and gives you elements in B. It's just abstractly so far, because of the definition, we're just working in a category. It's just like an arrow, whatever that means, a category arrow. So what should be the kernel, right? Because like, what's a kernel, right? A kernel is things that go to 0. So if we don't have things to go to 0, then we need to do something a little bit different. And this is what we'll do. So the kernel of F so it's an object K and a morphism, which I'm going to call I. I don't know if there's actually like a more canonical name for it. It's a morphism to A, satisfying the following universal property. And I encourage you, as while I'm saying this universal property, to sort of check it in your head with the usual notion of kernel that you know from sort of the more familiar stuff that you've been working with, to see if it's sort of see that it's compatible. So here's what you do. I'm going to draw on the bottom my map, my morphism A to B, and K is my map to A. And the first thing about the kernel is that it has to compose with F to 0. which makes sense, right? Because if you map from the kernel, if you map from the kernel into your object A, and then you apply the map that you're the kernel of, you should get 0. It's like everything in the kernel goes to 0, except we don't have things inside. We don't have elements necessarily. So the other like half of this universal property is that if I take something else, K prime, that also maps to A by I prime, and this composition, do I prime then do F, is also 0. So remember, when I say 0, I mean just like 0 in Hom, in A, K prime, B, because this is an abelian group, so it has a 0. That there should be a unique map from K prime to K, so that basically I prime factors through the kernel. Anything that's killed by F factors through the kernel is like the idea of this universal property, but it's sort of said in this funny way because we're kind of trying to be as general as possible. So, okay, this was just an example. I mean, I'm not going to use the universal property of kernels in anything I'm doing on the board, but any like questions about that? All right. Okay, yes. Okay, so that brings us to what I really wanted to show you, because I think is like super neat, which is this really general version of Schur's lemma, which is the Schur's lemma that holds in any abelian category. So let A and B be simple objects. So this is like standing in for our irreducible representations, but now they're just simple objects, and whatever that means in your abelian category. They could be R modules or sheaves or whatever. Then any non-zero map between A and B is an isomorphism. So same thing as before. This would be like our V prime. And I think this is really cool because like these are not necessarily representations or vector spaces or like anything like that, right? They're just something in an abelian category. And I want to show you the proof because, in my opinion, the proof is basically the same. Right? So you start with the fact that A and B are simple, so they have no non-trivial subobjects. And then you prove that the kernel of phi and the image of phi are subobjects of A and B, respectively. I wrote an arrow here instead of subset because these are not necessarily subsets, right? We're just being very abstract here. And kernel is defined in that weird way that I showed you before, and image is also weird. I mean, I say weird, maybe if you're a category theorist, it's very like, yeah, of course, but they're defined in this very categorical way. But whatever, the things that are kernel, that correspond to kernel and image in the most general, in this general framework, are still subobjects of A and B. And for a non-zero phi, we get that the kernel of phi is 0 and the image of phi is B. Yeah, and I have to say, even though I'm saying it's the same, like proving it by hand is a little different because like showing that the kernel of phi is 0, for example, you have to like draw some objects and arrows to get that to work, that kind of thing. But in essence, I still think it's the same. And what you can conclude from kernel of phi equals 0 and image of phi equals B, using again more properties of abelian categories, you can get that phi is actually an isomorphism. You can like get an inverse map, which gives you the proof of Schur's lemma in this general way. Yeah.
What is a subobject defined as in this context?
Yeah. So I think it's like an equivalence class of monomorphisms. So monomorphisms is like defined, I'm not going to get it right, but it's like either like it's like, I don't know, maybe it's like f of I equals f prime of I implies f equals f prime or something like that. Maybe the I is on the other side. This might be the opposite one, but it's some sort of like, it's the thing that stands in for injective map. And I think a subobject is like, okay, I'm not going to say what I mean by equivalence class because I would have to like look it up to get it precise. But if you have a notion of monomorphism, you can think about all the monomorphisms to A, and then you can think about which ones are equivalent to each other in some way that I'm not saying. And then that equivalence class, I think, is what's defined as a subobject. Yeah, I think most of the definitions I have here are from like when I was like working out these statements are from Weibel's book. So that's all in like the very beginning, maybe like section like 1.2 or something, if you want to look it up there.
Okay, thanks.
Sure. Yeah, okay, so that's the proof of Schur's lemma. And I just wanted to mention like one more reason why I at least would care about Schur's lemma in this general way, which is a corollary to Schur's lemma, is that if you take just one simple object instead of two, then in any abelian category, you'll get that the morphisms from A to itself form a division ring. So a division ring means a division ring D. So it's a ring that has the property that for any D in D, there's some D inverse in D. So it has a multiplicative inverse. I mean, so such that D inverse equals D inverse D equals 1, you know, the one in the ring. So like if this was commutative, it would be a field, but division rings don't have to be commutative. And the only difference between a division ring and a division algebra is whether you're thinking of it as, so what should I want to say? The center of a division ring it's the things that commute with everything in the ring, right? And because it's a division ring, so that means that commutative subset is actually a field. And so any division ring, I guess, is a division algebra over its center. So division ring, division algebra are sort of similar notions, depending on whether or not you're thinking about it as an algebra over its center. And the reason I'm maybe bringing up division algebras is because that was what Yael was talking about 2 weeks ago. So yeah, it ties in there as well. And just to prove that this corollary from Schur's lemma, so first of all, the fact that it's a ring actually does not have to do with Schur's lemma or the fact that A is a simple object. It just comes from the way that abelian categories are defined. So first of all, we know that hom A to A comes with an abelian group structure, and composition distributes over addition. So like what that looks like in this case is that if you have, you know, F plus F prime G equals F G plus F G prime, etc., you get that multiplication distributes over addition in the way you expect. So you get that hom A is a ring, that's just in general. And then the division part is what comes from Schur's lemma. So any non-zero element is invertible, which means that for every phi in this ring, there's a phi inverse, right? We have a phi inverse because phi is an isomorphism. So that's the same as being a division ring. So the reason I was even talking about division algebras, I guess, is because division algebras are what we think of as they're things that give us Brauer classes. So like basically what happens is that if you have any abelian category that you want, and you take any simple object, then you get an element in some Brauer group, which I think is pretty cool. It's sort of like a very, very broad and comes down into this very like interesting and like group that people actually study the elements of, So I don't know. I just think that's a very like cool fact as well.
That is bizarre. How do they, is there any way of like tracing back the field that it's an element, the Brauer group over, besides, I mean, like you could try to figure out what the maximal subfield or something, the center of this thing is, I don't know.
Yeah.
I don't know.
I don't know.
Bizarre. That's
yeah.
It's okay.
Yeah, it's pretty crazy, I think. Yeah, okay. So the last thing that I have as part of this talk is one example, because I wanted to do at least one example that was really not related to representations. But I also have a caveat, which is like, I'm not an algebraic geometer, and I read this book mostly to get this example. I read this part of this book, and I condensed it onto slides like according to my understanding, but don't put any facts in your thesis, like check the book if you want to be like 100% sure about these things I'm about to say. But this is what I think. I think that what I'm writing is all fine. But like I said, check if you want to like look at this in detail. So here's the setup. You start with a Noetherian projective scheme over a field. And I don't know if everyone here has like taken a class that has schemes in it or like remembers, but the idea is, so schemes are like a main topic that people, a main like object that people study in algebraic geometry. And Noetherian is like a property that makes them very, it's like a type of very like nice scheme. And a projective scheme over a field K is also a nice property. It's sort of like if you know about projective varieties, you can sort of think of a projective variety-ish. So whatever, we're not actually going to work with the details here. I think these are just the assumptions you need to make everything I'm going to say work. So this is an object that you study in algebraic geometry, or if you know what it means, then great. And if you're in the algebraic geometry class right now, then you recently learned about coherent sheaves. But so like we were saying before, a sheaf is something that takes open sets and gives you abelian groups. And coherent sheaves do it in this sort of interesting way that's a little bit like finitely generated modules. I don't know, it's both like very vague and kind of wrong, but something like that. And this dim E equals dim X is also a technical condition. I just didn't want to like not write it because of the things I'm going to say. I want them to be like, you know, true. And what is even the definition of the dimension of a coherent sheaf? I'll write it in case anyone likes algebraic geometry and like is curious, but I'm not going to explain it for if you don't have algebraic geometry. So if you want, you can like tune me out for a second. So the dimension of X, I think, is like the curl dimension, like the topological space dimension. And the dimension of E, well, like it's a sheaf. So what does that mean? So I think what you do is you take the, you want the dimension of the support of E, which is this support is the set of points in your underlying topological space such that the stalk of E at X is not 0. And then you look at the dimension of that again. So this ends up being a closed subset of X, and so you can think about dimension, and it's something like that. So those are some conditions. And the thing we're actually going to want to use is that for a sheaf satisfying all these conditions, you can define something called the reduced Hilbert polynomial. So this, I think, there's a notion of Hilbert polynomial for coherent sheaves that I think is compatible with like the other ideas of Hilbert polynomial. But the definition is also long and it also has like cohomology in it. So I did not try to piece it out exactly, and I did not put it on the slides. But the point is, okay, you have something called a coherent sheaf. We have this fixed base scheme X. We've got coherent sheaves, and for each coherent sheaf that has some properties, we can define this thing called a reduced Hilbert polynomial. And this is actually a polynomial, and it actually has rational coefficients. So it's not like anything too crazy. I'm not sure if it has integer coefficients. I didn't figure it out, but it definitely at least has rational coefficients. So there's that. It's a polynomial. And the reason that it's kind of good that it has rational coefficients is because we can compare them by comparing the coefficients. So like, what does it mean that a polynomial is bigger than another polynomial? So you could say it two ways, I guess. You could say that like asymptotically, if you go to like really high values of X, like you'll get something higher value for, this one will give you this polynomial will give you a higher value than this one for sufficiently large X. Or you can like think about it in terms of the like lexicographic ordering, I guess, the like comparing the coefficients. So like, for example, if you have like x cubed plus 2x plus 1, and then you have like x cubed plus 3x, what you do is you start with the biggest degree and you say, okay, well, x cubed is the same as x cubed, so you move down, there's no x squared, okay, 2 is less than 3, okay, so this one's bigger. I don't know, questions about that? It's just sort of like a way of comparing these polynomials. I'm actually not going to say what pure means because it's also just a condition that has to do with dimensions. But then you can think about these like, oh, that's an eraser, not a highlighter. You can get these semi-stable sheaves. So what happens is you look at subsheaves, proper subsheaves that are, it's like a sheaf with a map to E that I guess is injective on all the like open set pieces. And the point is that when you go down to a proper subsheaf, you don't get any bigger polynomials. So that's what it means to be semi-stable. And then there's a similar definition, which is stable. And the only difference is that instead of less than or equal to here, we have just strictly less than. So you can't have the same polynomial on a proper subsheaf. Okay, so there's all of that. These are some definitions we're going to need for our example. But why are we going to need it? So what happens is it turns out that on a scheme X, like the one that we have here, this Noetherian projective scheme, or maybe more general, maybe all schemes. But either way, the category of coherent sheaves on X, so that's things that are coherent sheaves and maps of sheaves between them, turns out to be an abelian category. And that actually is not the abelian category that we want. We want something a little bit more specific, which is the subcategory of semi-stable. So semi-stable means that P of F is less than or equal to P of E. So semi-stable sheaves with reduced Hilbert polynomial P. So we want just like E semi-stable and P of E equals P, and then the maps between them. This turns out to be an abelian category, which I am very much not going to prove. But the point is, this is an abelian category, and helpfully, the stable sheaves are the simple objects in this abelian category. So what we can conclude from this is that if you have two stable sheaves with the same Hilbert polynomial, so they're in CP for the sum P, and they're simple objects in that category, then there is a non-trivial homomorphism. Any non-trivial homomorphism between them is an isomorphism. This is just Schure's lemma again, but now it's for something sort of a lot more crazy, these stable sheaves. And as a corollary, for any stable sheaf E, then its endomorphisms are a division algebra over K. Just to be like technical, I'm not sure if the K actually has to be its center. I'm not sure how the book is defining it, but you get a division algebra. Yeah, okay, so that was my last example. Here are some references. I'm happy to go back to anything that anyone wanted more detail on in the talk or just take questions. Yeah, thanks for listening.
Thank you, Tamara. Great talk. All right, so any questions?
Sorry, I missed what was little k? Where did that come up?
It is, you have a projective scheme over K, I think. Let me go back.
Oh, okay.
Yeah.
That makes sense. I mean, I say that as if I know what the hell's going on. I can pretend.
Yeah. This is basically what's on the board is like more or less what I understand. Like, you know, there's a lot of gaps.
Yeah.
Right. So speaking of that page, you know, some side questions. So my mind is explaining what the word coherent means here. What was coherent here?
Yeah. Okay. So what's like a? I mean, do you know what a sheaf is?
I mean, you gave a talk.
Yeah. Okay.
Right?
Yeah. So
something, but not.
Yeah.
Everything, no.
Okay. So I think what I would say is like so if you start with a scheme, then there's an idea of what do I want to say? I'm just trying to figure out like how to put this in a good like
do the
order.
affine case.
Okay, yeah, that's a good idea. So yeah, so if you have something like X is equal to the spectrum of A. I don't know, does this like ring a bell, or is this like, what is that?
I mean, I looked at the definition before, but I mean, it's okay, right?
Okay. Yeah. So this is like a scheme that corresponds to a ring, let's say, right? There's some correspondence between certain schemes, which are called affine schemes, and rings. And then what you can do is you can think about, so this I'm writing X, but this is really like a pair, which is a topological space, and a sheaf, which is called OX. And in this particular case, this sheaf doesn't just map to abelian groups, but actually maps to rings.
Oh,
So yeah, so that's like the first like piece of the puzzle. And then what you can do is you can think of another sheaf, like F could be the name or something. I don't know. People use curly letters for sheaves a lot, but not this book. So you can think of some other sheaf, which is also a sheaf, sheaf on X. So again, you're like mapping to abelian groups, but those abelian groups now, for each open subset, the ring that you get from OX and the abelian group that you get from F, you get that the abelian group that you get from F is actually a module over the ring that you get from OX. So I think I'm going to cop out on giving like the whole definition of coherent, but the idea of coherent is that like you have this nice finitely generated module structure that sort of all comes from one module over one ring.
I see. So it's somehow compatibility, so to speak. Right? It comes from one single thing, that ring module, right?
Yeah, it's like
I'm saying the right words here.
yeah, I'm trying not to like say tons of like definitions in a row, because my experience with algebraic geometry is that a lot of times like there's something that people want to talk to you about, but it's like there's just like a lot of things you have to define to get there, you know.
Sure.
But yeah, the general idea is that it's like a almost like a module over a ring or a finitely generated module over a ring, but like it's with schemes that notion can get very complicated, and this is like a very nice one.
I see. Thanks.
Yes,
Sorry for the question. I mean, obviously.
that was good.
Algebra geometry. So, yeah, any other questions?
I was just wondering how the Schure's lemma translates for like simpler objects like vector spaces or groups. And I was thinking a little bit about this. I guess it translates to like very trivial statements in those cases. Like for vector spaces, it says that a map between one-dimensional vector spaces is either 0 or an isomorphism.
Oh yeah, I guess so.
And for abelian groups, I guess for maps between Z mod P are either like
Wouldn't you be
groups
able to
with,
do it for any simple group?
I guess it depends on what you mean by subgroup here, whether it's normal subgroup or just a subgroup.
Well, it will only be for abelian groups, so that particular detail
Yeah, okay, yeah.
won't be an issue.
So then only the prime order groups, and that just says that you can either have 0 map or isomorphism, I guess.
Right.
But-
I guess it's something that you would know already.
Yeah, but if not,
Yeah.
yeah, nice talk.
Thanks.
I think that's how they should prove it to undergrads in like abstract algebra 1. The only maps between Z1, PZ, Z1, PZ are 0 maps with the isomorphism via Schure's lemma and
Oh,
see what
man.
happens on categories and see what happens.
I'm sure that would go great.
Everyone will drop the class.
Yeah. Yeah. Oh, there was one thing I forgot to say, which is that I think that people study like things whose endomorphisms are division algebras. The implication doesn't go the other way. Like there's not like a converse that if the endomorphisms are a division algebra, that you necessarily have a simple object. But if you want to hear a buzzword, I think like exceptional collections is the thing that has to do with that. And there are other things that I've seen where people care about what the endomorphism ring of some object is. But Schure's lemma, I guess, gives you that type of object.
All right, any other questions? If not, let's thank Tamara again. Great talk, Tamara. So let me stop recording. There we go.